the gas chillers and NGL, natural gas liquid recoveries. Okay, so in general, the objective of this unit is to recover benzene and other heavy hydrocarbons. Benzenes and other heavy hydrocarbons, such as pentane and plus, from the treated gas before it goes to the liquefaction process. So in the gas chilling and NGL recovery process. So we're not going to talk about this specific process here, I mean, in more details. We just want to, we just talk, like in this slide, we just talk about the objective of this unit, the gas chilling unit. And but our main focus in this unit will be on main cryogenic heat exchanger. So the purpose of the NGL recovery is that we remove benzene and other heavy molecules, such as heavier molecules heavier than pentanes, okay, from the treated gas before we send it to the liquefaction unit. Why? Because the heavier molecules, they will freeze, they will be frozen in the main heat exchanger unit, because the temperature in that unit is too low. So we have to make sure that we are not sending heavy molecules with low, with low boiling point or melting point. Okay, so actually, what we recovered in that NGL unit, recovery unit, is we recover LPG products, okay, liquid petroleum gas, and we also recover a sufficient amount of ethane and propane that we will use it as a refrigerant makers, because propane and ethane, propane is used in the single propane refrigeration cycle, and also in the mixed refrigeration cycle we have propane and ethane as well, so we can use them as a makeup in that unit. So before we continue, I'm gonna just give you, that's why I open another slide here. So I just want to give you some better idea that where we are now. So, okay, just let me, yeah, this is not the good one that I have here. So just let me open the, okay, just let me open another one here. So now I have this one here, because I added some slide here to explain better for you what's going on and what we are going to talk about here. So yes, okay, that's good now. Okay, good. So here you remember in other unit in this course we talk about, you know, a pre-cooling system, that pre-cooling that we have, that we use single propane to cool down the dry natural gas coming from the dehydration unit. Then we send it to the scrub column, that we take our NGL, okay, NGL, natural gas and liquids, and then we will send it to the liquefaction unit. Okay, so we have one unit here between them that is used to separate the plus pentane molecules. Why? Because if you remember, in the fractionation unit, what we will do in the fractionation unit, we will remove we will remove until isopentane. Until isopentane. Okay, plus isopentane has to go to another unit to be removed. Okay, so this is like where what is we are talking about now in this slide. Okay, so okay, liquefaction unit. Our main focus will be here on liquefaction unit. So liquefaction unit, that is also gas chilling, all together, all the equipments together. So it has three key components. Okay, three key components. So let me go back again to this slide. This unit, all this unit together, what you see here, all of them are considered as liquefaction unit, gas chilling and liquefaction unit. So it has, how many components it has? It has three main components. One, feed gas pre-cooling, which is here. Feed gas pre-cooling, we have a dry gas. We have a dry gas that is coming from the hydration unit. It goes to the pre-cooling unit that is using only propane as a refrigerant, and it will be cold. Then it will be sent to the scrub column. Here again, we have a propane in this unit, and we remove natural gas liquids. Okay, and then we have our main cryogenic heat exchanger. This one that is using mainly mixed refrigerant for the cooling purposes. So this is the three main components of the whole liquefaction unit. So now, okay, I prefer to to open these two slides together because in this way I can explain better. So propane pre-cooled and mixed refrigeration process. So you see, you have pre-cooled propane, you have your feed gas coming to this pre-cooling system. That the blue one is the propane, it's only propane, and you see it is in contact with mixed refrigeration. So it's a unit that we have propane refrigeration cycle, mixed refrigerant, that is mixed refrigerant also has its own cycle, refrigeration cycle, and feed gas. They are all in contact with each other in this pre-cooling unit. So the use of a single component pre-cooling, and here in this part, the use of a single component pre-cooling fluid with a stage pressure let down provides an efficient and easy to control pre-cooling. So we are using only a single component or a single refrigerant. We use only propane here. Okay, it's a single component refrigerant that is easy to control and is efficient. And in another part, okay, we are using a mixed refrigerant. Okay, so here we use also mixed refrigerant. The use of this mixed refrigerant, okay, for the liquefaction and subcooling, because this mixed refrigerant is going inside the main cryogenic heat exchanger, that it goes to very low temperature, and it can provide a very good subcooling property. Subcooling means we have superheated vapor, saturated vapor, two-phase, saturated liquid and vapor, then saturated liquid, then subcooled liquid. So the use of mixed refrigerant for liquefaction and subcooling in a single heat exchanger permit boiling of the refrigerant over a temperature range leading to the high efficiency when it is most crucial. So it's saying that when we have a mix of refrigerant, okay, so each of them, is a mix of propane, ethane, nitrogen. So like each of these molecules, they have their own properties, they have own boiling points. So when we use such a mixed refrigerant, we can send it to the heat exchanger, where in that heat exchanger, like this main cryogenic heat exchanger, we have different zones, different temperature zones. At the top here, we have cold bundle. At the middle, we have middle bundle, and at the bottom, we have warm bundle. So when we use mixed refrigerant, so like each of these, components in the mixed refrigerants, they can be converted from liquid to the vapor or vice versa in each of this bundle, okay, depending to their boiling point and molecular weight. So in this way, the propane mixed refrigeration cycle minimizes the number of equipment and control loop. So like when we use such a configuration, when we mix a single refrigerant here with a mixed refrigerant in one single pre-cooling stage, and then in the main cryogenic heat exchanger, in this case we can minimize The number of equipments that we need, we just have one equipment that they are all in contact with each other. So we minimize the number of equipments that we have. That also minimizing the number of equipment means less operating costs, less maintenance costs, and in general, higher efficiency. And after that, okay. So another advantage, so less component, less equipment means minimal plant complexity. Okay, we have less complexity, which is easier for operation, and also the maintenance is less. It means high availability. I'm just checking something in the. Okay, I'm just just use this checking to see if I'm recording correctly or not. So this is not important because I'm already showing to you here. So feed gas precooler. So let's now start from each of them and then talk about each of them. So this is the precooler. This is the scrubber column. You know, in another slide that I showed you at the beginning of this video, so you can see this. You can see this scrubber column. Okay, that we get our NGL. Okay, and LPG. Okay, like from the bottom of the scrubber, we have some components. We have a stream that is sent to the fractionation unit when we have the ethanizer, the protonizer, the propanizer, and so on. And then it is sent to the, like in fractionation, like are separated. That then at the end we get our benzene and plus C5 molecules here, benzene and plus C5, because we don't want to send them to the main cryogenic heat exchanger since the temperature is very low. So let's start from here. The feed gas is cooled by a medium and low pressure propane, medium and low pressure propane in the feed gas medium, feed gas medium pressure propane, and feed gas low pressure propane evaporator. So we have a feed gas. So this three that you see, we have low, medium, and high pressure. Low, medium, and high pressure. They are like, you know, like inside, like each of these lines, these blue lines, they are connected to one evaporator. Okay, the evaporator that I'm talking about. Medium, low pressure evaporator, medium pressure evaporator, high pressure evaporator. We already talked about this in unit 4. So no need to, you know, go through the details. If you go to unit 4, you can see like how they are, like how they work, how they are connected. So the feed gas goes through the low pressure and medium pressure evaporator to get cooled, like in these two evaporator. Okay, so the evaporators are connected to the compressor, and then, you know, we have a condenser, and the cycle continues like that. So the cooled feed gas enters the scrub column at a temperature about -25 degrees C in a summer season and -29 in the winter season. So actually, like, this process that you are talking about is not is not a general unit it's not for about the general heat. Like this number especially, not about general LNG unit. Is a specific LNG unit, like this configuration. This flow diagram is taken from a specific LNG unit that unfortunately I don't know what's the name of that unit, but I can search and I can add this information later. But most of the LNG units, the majority of LNG units, they follow the same configuration, the same design, and these temperatures are almost the same in many LNG plants in many countries. So after the pre-cooler, the feed gas, which is here, it's reached to temperature -25 if you are in summer season, and -29 if you are in the winter. Then it goes inside the scrubber column here. Okay, after that, So after that, so like this is not what you see in this photo. Okay, it's preferred dry natural gas is pretty cool. So it's another step of you know, like here is talking about just one step of pre-cooling. Okay, let's say after the low pressure evaporator, it reached to 35, then lower temperature, and then in the high, in medium pressure evaporator, it reached to a lower temperature, and at the end, in the high pressure evaporator, it reached to minus 25. That then it exits and it goes to the scrubber. After a scrubber, okay, there are several streams here. The natural gas, okay, the gas will be sent to the main cryogenic heat exchanger. Main cryogenic heat exchanger, this one, that it will be liquefied, the natural gas, it will be liquefied and subcooled to a temperature between minus 150 to minus 162. Okay, so here it is minus 25. It goes through several steps, and at the end it will leave at minus 150 to minus 162 degrees C. Okay, and this is being done by using a mixed refrigerant through different bundles. Mixed refrigerant that we have here is vapor, liquid, so it goes through different bundles and take our natural gas from minus 25, and it delivers us a liquid natural gas at minus 50 to minus 162. So let me clean this part a bit here. Okay, good. Next, the scrub column, this one here. This column here is also a very important piece of equipment. So what it does, it removes benzene and heavy hydrocarbons, okay, that will freeze in the cold end of the liquefaction unit. So this scrub column here, it will remove heavy molecules like, like benzene and heavier than methane. So it will be sent to the fractionation unit, and then we will get our LNG, NGL, which is natural gas liquid, and liquid petroleum gases, like heavy molecules, heavier than, heavier than benzene and pentane, C5 plus. So why? Because we cannot send this to the main cryogenic heat exchanger because they will be frozen at the cold bundle. Cold bundle is somewhere here. So the heavy hydrocarbons from the bottom of the scrub column are fractionated to recover adequate amount of refrigerant makeup components and LPG to achieve the desired higher heating value. So here we remove what we remove here, not only heavy molecules, very heavy molecules, we also remove ethane and propane in the liquid in fractionation unit. In fractionation unit, as you have seen in other videos, we have the ethanizer and the propanizer. So we will remove ethane and propane from this stream. To first of all, we use this two, ethane and propane, as a makeup for the mixed refrigeration, because they are the components that we have in the mixed refrigerant. So those can be used as a makeup for the mixed refrigeration unit cycle. And also we create our LPG, okay, liquid petroleum gases that we can sell them. Okay, they have a very good heating values, and also when we remove them from the natural gas, so we can also adjust the heating value of natural gas as well. A scrub column bottoms are processed in the fractionation unit to produce 4 products. So at the bottom of a scrub column here, we send them to the fractionation unit to produce this 4 products. A LPG reinjection stream, an ethane-rich refrigeration makeup, ethane-rich refrigerant makeup stream, a propane refrigeration makeup stream, and NGL product stream. So NGL, LPG, propane, and butane, propane and ethane that will be used as refrigerant for the mixed refrigeration cycle. So you're already saying this now. Okay. So this is not something. Okay. So this is not something. I mean, important. It just shows that you see, like in this figure, I'm showing you 3 lines here. Is each of these lines are connected to an evaporator. Okay. So those are. I mean, like it can be 3 evaporators or 2 evaporators. Like here, I talk about low pressure and medium pressure evaporators. So it can be these 2 evaporators. That each of these evaporators they are connected to a suction drum, and after suction drum, they go to the compressor. So here we have suction drum, and then we have compressor. Suction drums are used to remove first of all liquid from vapor. So only vapor goes to the compressor, and also they are connected with a recycle stream from the output of compressor to avoid any surge problem in the compressors. Okay, this is, let me just maximize this. So now this figure, this slide shows different step of, okay, it shows different, okay, let me just bring this a bit down because maybe you won't see it in that video. So yeah, so the this figure shows the different level of temperature, okay, from warm to the cold. So let's maximize this a bit. Okay, so here you have at the beginning, so you have, I mean, several steps, okay, that you have your natural gas coming from the source. You have then, you know, like separation. I mean, like you have a separator to stabilize the natural gas, okay, and then you will send the natural gas to another unit, acid gas removal unit, and then you will send it to dehydration unit. And after that, okay, so here uh, after dehydration, you have a pre-cooler, propane chiller, or we call it chiller or pre-cooler. And after that, you will send after pre-cooler, you will send it to the scrub column. Okay, pre-cooler, then a scrub column. In a scrub column, you get your NGL, and that will be sent to the fractionation. And after that, to the main cryogenic heat exchanger, that you have your LNG at the end. Yeah. So from high temperature to low temperature. I mean, this is the main message of this slide. Okay. So okay, I'm gonna talk a little bit more about the scrubber column. This one here. So let's see what we have. This is a scrubber column with some more details. Okay, we have is not only one column. So a scrubber column is something like a distillation column. Okay, a scrubber column is something like a distillation column that will use that has like something like a condenser and reboiler that can separate light products from heavier products. The scrubber column is I think I put one of these slides. I put a video link for you, so a YouTube link, so you can see how a scrubber column works. A scrubber is like a packed bed, column. Okay, it's like a packed bed distillation column, and it has like a reboiler. It has something like I don't call it a condenser. It's called reflux drum that create the liquid. So you have your gas from bottom to the top, and you have liquid from top to the bottom. So this is the way that it will separate heavy molecules from, lighter molecules. So now let's see what we have. So this is a scrub column. The gas after pre-cooler, which is at minus 25, it goes inside the scrub column. And then in the scrub column, we have at the top, we have vapor. And at the bottom, we have our heavy molecules that goes to the fractionation unit. So at the top, we have a vapor, which is the overhead vapor from the scrub column is partially condensed in the warm bundle of the main cryogenic exchange. So we have at the top the vapor that is at temperature about minus 39, and it will be sent to the warm bundle of main cryogenic heat exchanger. Okay, so it goes to the warm bundle of mix of main cryogenic heat exchanger, and it will be condensed in the warm bundle. Warm bundle is not like 80 degrees C, 100 degrees. Warm bundle is minus 50, minus 40, something like that. In cryogenic process, warm doesn't mean that is like warm like Kuwait, like Qatar. Is like we are talking about very low temperature, minus 40, minus 50 is still warm in the cryogenic process, right? So the warm bundle, so it goes inside the warm bundle, and it will be back, it will exit in the two-phase. The two-phase stream exiting the warm bundle of the main heat exchanger is separated in the scrub column reflux drum. So it goes to the warm bundle, we don't see it here, it's somewhere here in the heat exchanger, and it comes back two-phase. It comes back two-phase here, and is now vapor and liquid, so it will be sent to the scrub column reflux drum. Okay, we call it a scrub column reflux drum. That in this drum, we remove vapor from liquid. Okay. The vapor returns to the main heat exchanger middle bundle, and the liquid is used to reflux the scrub column. So this reflux drum, okay, it does the same job that the condenser do for us in the distillation column. So it will remove liquid from vapor for us. Vapor at the top, it will be sent to the middle bundle of main cryogenic heat exchanger, and the liquid will be pumped to the scrub column, because this is a cold liquid that we can use it to separate some heavy molecules in the scrubber column from this natural gas coming, the feed gas. The reflux temperature is controlled at minus 51. Okay, so the reflux here, we have the reflux, the temperature is about minus 51. That's why you see that here your gas is coming at minus 25, but it leaves at minus 39. It is cooled down. Why? Because we have a reflux liquid here that is at very low temperature, minus 51. So when it goes inside this scrubber drum, it can cool down the natural gas to this temperature. So we can control this temperature by adjusting this stream here. We have a valve here. So the gas, the natural gas, that is sent to the warm bundle, we can take a bypass stream here, and we will mix this bypass stream with this stream that is coming from main cryogenic heat exchanger, and then we will send it to the reflux drum. So in this case, by changing this flow rate here, that you see it has a thermocouple that measures the temperature, and then it can play with this valve. So in that way, because we have a minus 50 something here, and we have minus 40 here. So when they are mixed, we can adjust the temperature something between 50 to minus 40 to minus 50. So by passing the warm bundle with a portion of the overhead vapor from the scrub. So from what we can do from a scrub column, we have a vapor that is going to warm bundle. We can take a side stream bypass, and we mix it with the stream that is coming from the warm bundle of main cryogenic heat exchanger to adjust this reflux temperature. Then okay. So let me clean it a bit here. because I don't want you to be confused. So then the vapor from the scrub column reflux drum, scrub column reflux drum, the vapor is here. The vapor from a scrub column reflux drum is condensed and subcooled in the high pressure feed circuit of the middle bundle of main cryogenic heat exchanger. So we will send this vapor to the middle bundle of main cryogenic heat exchanger, and it will be cooled down and it will be converted to two-phase in that bundle. And then the inlet, okay, so we already talked about that. This is the inlet temperature of the feed gas to the scrub column. Okay, we already talked about that in the summertime is -25, in wintertime is -29. This is not important. So we already talked about it. So it's talking about this temperature here. Then, okay, scrub column, as I said, is like a heat exchanger. We have an upper part, which is a reflux drum. We have a lower part, which is a reboiler. We have a kettle type reboiler here. Okay, so that is producing vapor for us, because we are separate in the scrub column. We are separating the heavier molecules. Those are the heavier molecules here from the natural gas that has light and heavy molecules. Methane, we want methane to go to the heat exchanger. We want the heavier products to be collected in other parts. So we have it's like a distillation column. We are separating heavy molecules from, light molecules. So here we use a reboiler, like a distillation column. So the reboiler temperature of a scrub column is controlled by the resetting the low pressure steam flow rate to the U-tube bundle of reboiler. So it's a reboiler. It has tube side and shell side. In the tube side, we use steam. We use low pressure steam in the tube side. So if we can, yeah, it's like this part here in the tube side. So we can play with the flow rate of this steam here by using this valve, for example. We can play with this flow rate, and in that case, we can adjust the temperature, the bottom temperature of the scrubber, which is 73. So this is the low pressure steam. We have two valves here. We have valves for this low pressure steam that is going to the scrubber. So how we can adjust this valve? So it's connected to a thermocouple measurement. We measure the temperature at the bottom of the scrubber. Then if the temperature is high or low, we can adjust this valve here, and we can change the flow rate of the steam. In that case, we can adjust the temperature at the bottom of the scrubber, which is usually about 73 degrees C. Okay, now we are going to talk a bit more. So we already talked about the scrub column. So now we are going to talk a little bit more about the main cryogenic heat exchanger. Okay, so this is the main cryogenic heat exchanger that we have. So there are not too many companies that are fabricating such a heat exchanger. So Air Product is one of the most famous. I think it's an American company. I don't remember. The only thing I remember from Air Product is that when I was doing my PhD, so I had to order some oxygen, some cylinders of oxygen and nitrogen. Like the big cylinders for our experimental work. Then I was looking for a supplier in Montreal. Then I found several companies, and one of them was Air Product. Air Product has branches everywhere in the world, and their main work is liquefaction. Like the liquefaction process, the cooling process, cryogenic, heat exchanger, and so on. So the main cryogenic heat exchanger is the heart of this natural gas liquefaction. The heart of LNG process is this heat exchanger. Is a very advanced heat exchanger. It has a very beautiful design, as you can see here. And Air Product MCR heat exchanger is one of their, license, one of their brand is. It has proven that it can provide us with a very good mechanical design, and it has a very high quality. You see like one of the photos here. It's a very big heat exchanger. You see it's like as tall as a tower. So it's like very well fabricated, and it has proven that it can provide us a very successful operation in the LNG process. Many countries are using it. So it consists of one or more spiral wood tube bundles housed within a single pressure shell. So it has a shell, this white part you see here at the picture below. So this is a shell. The white part is shell. So inside this, what you see, we have these photos here in the left side. So we have tubes of different bundles. Like each of this circles are the inlet and outlet of the different bundles. So we have usually 3 bundles, warm bundle, middle bundle, and cold bundle. So we should have 6 of these circles. Okay, maybe in this photo is not obvious, but we usually have 6. Okay. Then, the tube bundles are made of a small bore aluminum tubing. Each of these tubes that you see, each of these small tubes here, okay, they are made of aluminum. Okay, they are aluminum tubes, okay, and they can produce a huge amount of heat transfer area in a compact unit. It's a very compact unit but it can produce a huge amount of heat transfer surface for us, because we have many of these tubes here. So using a small tubes has this advantage that we can increase the heat transfer. We can increase the heat transfer area, right? And it's a compact unit, and it can work also at high pressure operation. That is very good for the efficiency of the process. It's very important for the efficiency of the process, and as well as the safety. Okay, you already saw this. So we have this kind of heat exchanger. Okay, we call it coil wound heat exchanger. We have also plate fin heat exchanger. We're not going to talk about this type of heat exchanger, but this is also another type of heat exchanger that is used in LNG plants. I'm not going to talk about it for now because our main focus is going to be on this side. But they have kind of different design, but both of them are proven that they have a good efficiency. Okay, so main cryogenic heat exchanger. Let me go to this. Okay, main cryogenic heat exchanger. Okay, as I said, is like usually is the one that is made by MCR, is made by Air Product Company, and it has 3 aluminum tube bundles. It has 3 bundles. This is the first bundle. This is the second bundle, and this is the third bundle. Warm bundle, middle bundle, and cold bundle. It has 3 bundles of aluminum tubes inside in a vertical aluminum shell. So all these tubes are inside the aluminum shell. Each bundle consists of a coil and fine bore tubing, which are arranged to maximize the heat transfer in the bundle as shown in the following slide. So like each of this bundle, it consists of several tubes, coils, we call it coils or tubes, that are designed to give us a very high amount of heat transfer area. Okay, so you have this. Okay, now let's go one by one to each of these bundles and talk a little bit about these bundles. So the first one, warm bundle here. We are talking here at the bottom. So the warm bundle consists of coils containing. So we have 4 coils, 1, 2, 3, 4, right? So first, high pressure feed gas from the scrub column overhead. Okay, where is your scrub column overhead? You remember we were sending the scrub column overhead to the warm bundle. Okay, so this is the first one. High pressure feed gas from the scrub column overhead. This is the first one. Second, LPG reinjection. Okay, so when we receive the LPG products after fractionation unit, we can send it to this one bundle. Okay, to this is like this is another stream. Mix refrigerant vapor from high pressure mixed refrigeration separator. So mixed refrigerant vapor is here. Mixed refrigerant vapor that is coming from mixed refrigerant separator, the high pressure separator. And finally, mixed refrigerant liquid from high pressure mixed refrigeration separator. So we already talked about these two before in other units, unit 4 in more detail. So we have one bundle, second, third, and fourth last one, mixed refrigeration liquid that is coming from high pressure mixed refrigerant separator. The one bundle cores are cooled to approximately minus 40. So the one bundle here is almost minus 40. Then we have the middle bundle. Okay, so I'm gonna just clean this. So middle bundle is here. The temperature of middle bundle is about minus 120. So again, we have 4 parts here. 1, 2, 3, 4. First, high pressure feed gas from the scrub column reflux drum. You remember the vapor from scrub column reflux drum was sent to the middle bundle. Is this one here? The vapor from reflux, no, the vapor from the reflux drum, the top of the reflux drum is not a scrub column, it's a reflux drum. Is here. Then LPG reinjection from the one bundle. So LPG reinjection it goes first to the one bundle and then it continues to the middle bundle. Then mixed refrigeration vapor liquid from the warm bundle. So mixed refrigeration vapor goes to the warm bundle first, and now here it will be cold, and here it will be condensed as well. So it goes then to the middle bundle. Now it is both liquid and vapor because it will be condensed. So here is vapor, now here is vapor and liquid, and finally mixed refrigeration liquid from the warm bundle. So mixed refrigeration liquid goes first to the warm bundle and then to the middle bundle. The temperature, as I said, is about minus 20. And finally, we have cold bundle. Okay. Finally, we have cold bundle. We are talking about here. Temperature of cold bundle is minus, don't forget, this is minus 150, 149, and pressure is about 18.3 bar. It's very high pressure, so like temperature minus 50 and pressure 18.3, minus 150 and pressure 18.3. So what we have in the cold bundle, high pressure feed gas from the middle bundle and LPG reinjection from the middle bundle. So LPG reinjection here, it goes to the warm bundle, middle bundle, and then cold bundle. We have also high pressure from middle bundle. So we have high pressure gas that is coming from the reflux drum. Okay, high pressure gas. This is coming from is a vapor from the reflux drum that goes to the middle bundle and then it goes to the cold bundle along with the LPG reinjection unit. Reinjection stream. They are all together and then they go to the cold bundle and mixed refrigeration vapor liquid from the middle bundle. So from the middle bundle, I had only vapor, mixed refrigeration vapor. Here I have mixed refrigeration vapor and liquid, and at the end, both of them, vapor and liquid, they go to the cold bundle. Okay, so this is what's happening in each of these bundles. Okay. So we already talked about this part in the, I think it was unit 6. Okay, unit 6, that was what nitrogen reinjection unit. In nitrogen reinjection unit, we have a Joule-Thomson valve that after the valve, we will send the gas to the flash gas, to the flash drum. In the flash drum, the temperature reduced to like something minus 40. So like this cooling that you see, like the cooling that you see is coming from the gas that is coming from flash drum. In the nitrogen rejection unit, we have a vapor that is coming from the flash drum at very low temperature, minus 60. Temperature is almost 1 bar. Temperature is very low, minus 60. This flash gas goes to the heat exchanger. We call it also cold box is a heat exchanger. Heat exchanger. So this was a fuel gas, right? This is the fuel gas that is coming from flash drum. The fuel gas at very low temperature goes to the cold box. This cold box or heat exchanger between mixed refrigerant, the green line, and fuel gas. So then this fuel gas will be heated, will be warm up to from minus 60 to minus 36, minus 160 to minus 36. And the mixed refrigeration will be cold from minus 34 to minus 160. Okay, and so like this is what's happening. So the flashing mixed refrigeration liquid through a Joule-Thomson valve into shell of the heat exchanger from the following distance. So we have subcooled mixed refrigerant from the high pressure mixed refrigeration separator. So let me just clean this here a bit. So this so mix so I mean, like we provide the cold. We provide the cooling by several methods. First one, subcold mixed refrigeration liquid from the high pressure mixed refrigerant separator. So this is a liquid mixed refrigerant liquid that goes to the warm bundle and then middle bundle, and then we have a valve here, Joule-Thomson valve, that we drop the pressure. In this case, we can drop the temperature, and then like after that, the temperature is very low. Then we will inject it to the middle bundle again. So we use this cold temperature here to cool down some other steam. Then, okay, so this is the first one. What's happening here to how to create a cold. Then, mixed refrigeration vapor cooled and liquefied in the coils. So mixed refrigeration vapor here goes to the heat exchanger first, and then we have also a valve here that we can drop the pressure, and we use that cold temp. Once we drop the pressure, we can drop the temperature, and we can create cold temperature, and we use that cold temperature in the cold bundle. Then mixed refrigerant vapor, cooled and liquefied in the fuel gas mixed refrigeration heat exchanger. So we create cold first by using this heat exchanger. We use this mixed refrigerant vapor. We send it to the mixed refrigerant heat exchanger, the cold box, and then the Joule-Thomson valve. In both ways, we can create a low temperature in this by using this. Then we have few more stuff. Okay, the main the mixed refrigeration liquid from each bundle are fed into a separator and distributed evenly over the respective tube bundle. So the mixed refrigeration liquid. So you see, like, okay, for each bundle are fed into a separator and then distributed even over. Okay, so like you see the mixed refrigeration liquid, this one here. So it will be first sent to the separator, and then it will be distributed evenly between each of this each of the two bundles. Okay. Each separator has a manual drain valve which can be used to adjust the mixed refrigeration composition if necessary. So this is not something very important or critical, just saying that how we can adjust the composition by just adjusting the valve. But just adjusting the valve, we can change the composition. It's a manual valve. Warm mixed refrigeration vapor at minus 37 and 31 is routed from the column shell through a 62-inch line near the base to the low pressure mixed refrigeration cycle. So the warm is talking about this part here. Talking about this part. The vapor, okay, the warm mixed refrigeration vapor at minus 37 and 3.2, okay, is routed from the column shell, because this is the shell of the column, shell of the heat exchanger, routed through a 62-inch line near the base, so at the bottom, to a low pressure mixed refrigeration cycle. Since it's the low pressure, so because the mixed refrigeration that we will send it to the mixed refrigeration unit to cool it down again. So in the mixed refrigeration unit, you remember we had first suction drum, then evaporator, then compressor. So this goes first to the low pressure suction drum and then to compressor. The overall height of the main cryogenic heat exchanger is approximately 60 meters. So this is very important information. The overall height of this mixed refrigeration heat exchanger is about 60 meters. Okay, then the cold box, the heat exchanger or cold box contain an aluminum core. So the cold box here, this cold box, I'm talking about this one. This heat exchanger, okay, we call it cold box or fuel gas mixed refrigeration heat exchanger. Fuel gas mixed refrigeration heat exchanger or cold box. This heat exchanger, this cold box, it has an aluminum core and cools mixed refrigeration vapor on one side from minus 37 to minus 160 at 47 bars. So it's a heat exchanger. In one side we have mixed refrigerant, vapor mixed refrigerant, vapor mixed refrigerant, that is at minus 34, about 47, 48 bars. It goes to the heat exchanger and it leaves at minus 60 and almost 48 or 47 bar, and then it goes to the main cryogenic heat exchanger. Flash gas from the LNG flash drum. This is flash gas, or we call it also fuel gas. This one here. It's coming from nitrogen rejection unit that is coming, the vapor that is coming from a flash drum is at a very low temperature. So this flash gas, okay, we call it flash gas or fuel gas, is coming from LNG flash drum. It passes through the other side of the cold box and it comes at minus 160 degrees C, and it leaves at about minus 36 at pressure 1.1 bar. Arrives at minus 160 and leaves at minus 36. Okay, and then it will be routed to the low pressure fuel gas compressor, because the flash gas or fuel gas, then we will send it to the fuel gas storage. First, two steps of compression. We already talked about that in Unit 6 in nitrogen rejection, and then it will be sent to the storage. It's the fuel gas. Okay, so this the cold box. Okay, so it's like we need a very good isolation inside this unit, the main cryogenic heat exchanger. So we should have a very good isolation, because we don't want to lose any cold. We don't want to have, because the ambient temperature for sure is higher than the temperature inside this bundle. We don't want it to lose we don't want to get like the bundles to get heat from outside, okay? And even this piping, they should be very well isolated. So the isolation mainly is done by polyurethane, okay? Polyurethane is like this kind of foams that, like even some foams that we use at home for washing dishes, they have kind of similar materials, okay? There are polyurethane, like this kind of foam, or glass foams. Glass foam are also used for isolation. This is one way. Alternative isolation is that we use a cold box. This cold box is something like that. Is different from the other cold box that you see here. It's a really heat exchanger. So, another alternative instead of using this foam is using such a cold box, okay, that is made of a normal carbon steel plates, okay, and it keeps the cryogenic equipment and piping. So like we put all this piping, cryogenic equipment, everything in the cold box, and then we will, all of them in the cold box. We don't let them to. This is not exactly what they use in LNG. It's just one example of cold box. So we put all the pipings and all the equipment in the cold box, and we isolate it, and we fill the void space between the piping, between the equipment. We fill it with the isolation material that like perlite. Perlite is a mineral powder. Okay, perlite is a mineral powder that, as you see one photo here, so it's used to fill the free space between the piping and equipment in the cold box. Okay, so those are some final slides that we have. Okay, advantage of the cold box. The cold box that I was talking about, advantage. The cryogenic process equipment and piping are all welded together, okay? So they're all welded, that make them as compact as possible. So when we have a compact equipment, that results in the minimal material consumption and also minimum thermal loss, and that means like a good efficiency. And also when we have a compact equipment, the operating pressure can be high, and the safety will be also maximized. The cold box can be constructed mechanically in the workshops in the optimized condition. It can provide us with the external mechanical protection. Okay, we can have external mechanical protection during the transportation, as well as inside the plant. Okay. So apart from the all welded principle, so which helps to the better safety and efficiency, minimum amount of material to be used. So this is one advantage. Apart from this, okay, that also it also provides a very safe installation. Okay, so the cold box can also provide us with this feature that we can detect the possible leakage. How we can do it? We can use a pulse flow of nitrogen through the fertile isolated space. So we send nitrogen, which is the inert gas, we send it in the pulse way, and then the pulse flow, and then we can, in the other side, we can detect the nitrogen. Like how the composition has changed, or how the flow, the pulse, the response that we get. We can analyze those response, and then we can see based on some analysis, specific analysis, we can see if there was any leakage or not. Okay, and also another advantage of cold box is that we can have, if we need a fire-resistant material or requirement, okay, we can also construct cold box in the efficient way that can meet this requirement, fire-resistant requirement. Okay, as a summary, what we saw in this, what we saw in this unit was Let me just make it smaller. Okay, what we saw in this unit is we saw that okay, the mixed refrigerant, propane and mixed refrigeration liquefaction process. It is proven. It has proven to be a reliable, economic, and efficient method for liquefying the natural gas. Okay, so it's a very efficient method, especially nowadays that the natural gas, the LNG, LNG process, energy plants, they require a broader range of process requirements than before. So the clients ask for better quality products, environmental issues. There are several environmental issues that the governments they put a lot of restricted I mean like uh, environmental conditions, to protect environments. So those are all affect, like the design of new plants. But using such a unit like propane and mixed refrigeration, liquefaction unit, it can still provide us all the requirement that we have from the customers or, different agencies. So, and there are numerous technology advancements that has been made that allow us to meet the demands for the larger train capacity these days. Like we have more customers, the consumption is more, so we need a higher capacity, production capacity, and like we can operate in different kind of climate, low temperature, high temperature. We can also provide different heating value products. Some countries like US and UK, you remember before that we talked about UK, that they were mixing the LNG that they are receiving with nitrogen to meet the requirement that they have, let's say, in their heating appliances, home appliances. So, like we have to have this flexibility to play with heating value of LNG, either higher heating value or lower heating value. So we have to be able, flexible, to play with those to meet the requirement by countries like US, UK. So this can be done by optimization the process. We can optimize it to extract, to extract hydrocarbons, lighter hydrocarbons from heavier ones, either in the upstream liquefaction process, okay, or integration of the liquefaction process by some other units. This can be done. So that was all for this unit. Thank you for your attention. I hope you enjoy it. And please let me know if you have any question. I will be more than happy to answer. Thank you, and I will upload the next unit soon.